Okay, in this video, I'll show you how Robert Bonavito's claims about using Benford's Law to show that there's some fabrication of the COVID-19 cases and of the 2020 election results are just totally absurd, and show that you have to use statistics properly in order to come to these conclusions. Okay, and so I found those videos quite disturbing because of how inaccurate they were. And so I'm going to show you why they're wrong, and also why how you can analyze the data better for the case of COVID-19. At least I'll show you. So he looked at the 50 state COVID-19 cases and was trying to use this thing called Benfords Law, which tells you something about the distribution that should occur of the first digits of numbers when you have a data set. And he said, oh, look, here's what I'm getting as my distribution of the first digits of the numbers. And it's not matching Benford's Law. Therefore, there's something suspicious going on. The main problem with this is he was not using any sort of analysis, statistical analysis, to understand what sort of errors from Benford's Law he should expect. And some of that stems from the fact that he only has 50 data points. Now, you can do statistics on 50 data points, but you have to do it properly, right? And it gets easier when you have more data points. And so I'm going to do it with more data points in a second. But he also did this for the 2020 election results for Pennsylvania. Again, only 67 data points. He said that both the numbers for Biden and Trump looked misleading. And so, yeah, this was just totally messed up and a pretty naive view of how math and statistics work. So, I had to kind of respond to this because I didn't like what was going on. So Benford's Law basically says that if you have a uniform distribution of numbers, and it's a quantitative data set, okay, most of the numbers are more than you would think. Okay, about 30% of the numbers start with the digit 1, and there's a mathematical reason for this. And actually, a fewer number of the numbers will start with the other numbers. Okay, so number 9 is actually the least common for you to start with that. The reason is because if you go from 100 to 199, let's just say, that's about a doubling. Okay, that has to occur, about a doubling, right? But if you go from 900 to 999, that's only about an 11% increase. And so the band, okay, of values, if they're quantitative values, from 900 to 999 is much less than from 100 to 199. So that's the origin of this law, and it's just a very simple consequence of that. A few things. You have to have a data set that is quantitative. You can't use this for telephone numbers. And as soon as I heard him say you could use this for telephone numbers, I knew there was a big red flag, right? He said that in one of his videos. You can't use this for telephone numbers, for example, because those are labels. Those are just labels. There's not a meaning to a numerical meaning to having a telephone number. It doesn't mean a quantity. Okay, it's a label. You can't use this for street addresses. You can't use this for Benford's Law for social security numbers. Okay, and you have to have a uniform distribution, and so that's a little more tricky to figure out. But there's ways to do that, and I'll show you a test of how I did that when looking at the COVID-19 cases. And you also have to have data that spans a wide enough order of magnitude. Okay, so you have to have ideally several orders of magnitude that your data's going on, and I'll show you where that can break down if that doesn't happen. So if I go to pull up my Excel document, what I did for the COVID-19 cases is I looked at the county data, because now when I have, this is just pulled from the CDC website, now I have over 3,100 data points instead of 50 or 67 data points. And so already I know that's going to be a lot better data. And then I looked at 6 different attributes. Okay, from the CDC website, I took the total number of COVID-19 cases thus far, total number of deaths, and then also, just to show you some things, 7-day average cases, so average cases over the last week and average number of deaths over the last week for each county. I also looked at population of each of the counties and water usage. Okay, this is in acre feet per year. This is how much water each county uses. This seems random, right? And what I'm going to be using these two for, population and water usage, is actually as just a control. These are kind of like my control experiments. And we'll see what the distribution is of those. They should follow Benford's Law. Then from that, I go to this next data sheet called first digits, and I use the same formula he used, equals left, and took the data and the first digit. So it's taking the leftmost digit of each number for those different attributes and for all the counties. And then I calculated what the distributions are of those different digits. And so you can see here's what Benford's Law predicts that ones should occur 30.1% of the time, nines should occur 4.6% of the time, and all the other digits somewhere in between. And then I did that for all the attributes and calculated it from here. I counted how many occurrences that were there and divided it by the 3,104 different occurrences. I had to subtract off if there's any zeros because then that's basically no data. And so when you do that, you get the following plot, okay? So this is COVID-19 cases per county using county data, right? Cumulative cases and cumulative deaths. And you can see it's very nicely fitting the red points with the blue points. The red points are the COVID deaths and COVID cases versus the blue points, which is what Benford's Law statistics predicts. You can see they're very nicely matching. Now, how do I know that they're matching, within statistical significance? There's more sophisticated statistical tests that you could do for this. I did something just very simple, but I want to just stress that Robert in his videos failed to do this at all. He saw two different plots, right? He got this plot for the 50 state COVID-19 cases, and he did that correctly, but he didn't, and he said, oh, this is different than Benford's Law. Well, yeah, everything is going to be different from Benford's Law. That's a statistically uniform distribution. This isn't a perfectly uniform distribution. There's some error. And he said, oh, they're different, so therefore something's wrong with it. But how do you know if it's statistically significant difference, right? And so a very simple way of doing that is going to some data that you can trust, that you think has the same number of sample points, that won't be fabricated, right? Or that's not going to be fraudulent. So that's what I did here. That's why I looked at population data and water usage data. I think it's very unlikely that the Census Bureau is going to fabricate how much water people are using or what the population of different counties are. I think we can trust that data. If we can't trust that data, I don't know what you can trust, and then you might as well just believe anything, right? But let's just say if we go under the hypothesis that we can trust the population and water usage data, then we have a test. We can figure out how far those values are from what Benford's Law says, and we can compare that to the COVID cases and see if there's a statistical difference. And so you can see these numbers are very close to Benford's Law as well, population number. So 30.3% for the number 1 versus 30.1%. Now it's not exactly right? Because there's always some statistical error. So what I did is then I calculated for each of these, how far away is the calculated value, the found value, from what Benford's Law predicts. And so for this first digit for population, number 1, it's 0.2% off, right? For water usage, it's a little bit worse. It's 30.8 versus 30.1, so it's 7% off. So I calculated the difference between those, took the absolute value of the difference, and then for all 9 digits, took the average error. And so what you can see is, on average, the digits for digit distribution for population is 0.4% off. For water usage is 0.7% off. So that tells you naturally, just within this data set that's this big and this type of data, this county type data, you're going to get roughly an average error of 0.4 to 0.7%. And if you get that, well, then that's fine. That's just normal statistical error. Look at what you get for COVID cases, cumulative cases, 0.5%, right within that error. Nothing suspicious about this at all. Now, there could be problems with the data that aren't caught by this high-level analysis, and I'm sure there are, but you can't say that Benford's Law points to any red flags, okay? Same thing with deaths. We're at 0.6% average error. That's between 0.4 and 0.7%. Now, I wanted to show you some cases where it could break down, right? Look at the 7-day average cases. Now the average error is 0.9%. Why would that statistical error be higher? It's because we don't have a large span of data, okay? Remember I said that the data has to span a large order of magnitude, okay? And so now we're just, it's close, but we're outside of the normal error range of 0.4 to 0.7%. Look at the 7-day average deaths, absolutely terrible, 11% error. And why? So this is a good one to show you, why these ones that don't have a large order of magnitude would be skewed. You have almost 50%, almost half of your counties only reporting 1 death in the last week. And so that's skewing all of it towards the digit number 1. And so you just don't have uniformly distributed data. It's lumped towards very few deaths, right? And same thing for the cases. You can see it's going to be off, okay, more. But yeah, so you have to take into account statistical significance. What is the error of your measurement, and what type of error? When is something within error? When is something without error? I'm a scientist, so I do all this stuff all the time. I can't come to any conclusion unless I know what the error is and of the experiment. This is a statistics experiment, but still an experiment, right?